So, how does the computer actually determine what bytes in the random access memory to read as instructions? And once it's read an instruction, how does it know what to do next? Well, that's the job of the program counter. The program counter is a pointer to a location in the random access memory of the computer, telling it which 4 bytes to read in order to determine an instruction. And then it is incremented by 4 bytes to move it further along in the sequence so that it can read the next 4 bytes to know what the next instruction is. And it continues on in this sequential method normally, unless it encounters something like a jump or branch instruction. Now, these instructions actually contain a new memory location to go to that would be out of sequence from the normal next 4 bytes sequence that the computer normally runs. Now, this new address then would tell it where to begin execution of the next instruction and then continue on in order, 4 at a time, unless it encounters yet another jump or branch instruction. So let's look again at a very detailed explanation of how the fetch execute cycle is to work. And we're going to again consider the add instruction or a similar add instruction to what we talked about earlier. So we look at the control unit and we see that it contains the program counter, and the number that it is pointing to in RAM memory is 2200. So it's telling it to go and begin execution by reading the instruction starting with byte 2200 from RAM memory. What the computer then does is fetches that 4-byte code and loads it into the decoder circuit that is going to be used by the control unit to basically pull apart the components of the instruction to figure out what it needs in order to execute. So we see the fetch occur here, and the information is loaded into the decoder circuit. At that point, the decoder will find out which byte contains the memory address of the data's source operands, what kind of a function the instruction calls for, in this case an add, and then where the result is going to be returned to the random access memory after completion of the instruction. So we see that here. Again, the ALU circuits are loaded up with the information that has been decoded from the add. It knows it's going to do an add function. It knows these are the operands that it's adding together, at least the location of the data, and the location where the result will be returned to. Next, the bits that represent the data to be added together are actually read or copied, because none of the data is actually destroyed when we read it. And the bits then are loaded into the ALU circuitry that is going to be used to add. So the 42 in this case is read from the memory location 428. The bits that represent 12 are read into the ALU circuit as the second operand, and then they're going to be added together. So the ALU takes over the execution portion of the sequence. So again, we've done instruction fetch, instruction decode, data fetch, and now the execution. So the last part of this then is to take the sum, where the result of the math is held, and to copy that. And notice we've incremented the program counter already to look at the next instruction in RAM memory. But the bits that represent the sum of the ALU addition function then need to be returned to the random access memory, where they're set up as a destination. So the information now is stored, the 54 is stored back into the random access memory at location 800 as specified by the instruction. So computers actually can only perform about 100 different instructions. These are referred to as primitive instructions. And all computers, no matter how sophisticated the software they're running is, breaks down into these small about 100 instruction primitives. And that's pretty amazing when you think about all the different things that computers can do. They can do high-end games, they can do computer-aided design, they can be used for creating, documents like term papers using Microsoft Word, and they all seem like they're very different applications. But again, they all can be condensed down into these small primitive operations that they all share. Besides doing addition, multiplication, and division, they can also shift bits. They can also compute using logical operators like AND and OR. They can also compare data values. They can check values to see if they are 0 or non-zero, jump to new locations based on the outcome of these tests, move information around memory, and of course read and write information to and from peripheral devices like keyboards and monitors. So computers, they get their impressive capabilities by being able to execute these huge numbers of these simple or primitive instructions per second. The computer clock determines the rate that the fetch execute cycle actually executes in. It's measured in gigahertz or billions of cycles per second. Let's take a look at, again, this computer, the one that I'm recording on, and we can see that the processor's clock speed is the CPU is at 2.2 gigahertz. That means that it can start a new instruction within 2.2 billionth of a second from one another. So that's incredibly fast. It can run 2.2 billion instructions per second, then is another way to say it. When we talk about in computer information systems, either very small or very large numbers, we typically use the prefix of, for large numbers, kilo, which is 1,000, mega, million, giga, billion, tera, a trillion, so on and so forth, to represent very large numbers. And we use the prefix of milli for small numbers, thousandths of a second, millionths of a second is micro, billionths of a second is nano, and so on and so forth. Modern computers try to start an instruction on every clock tick, passing off finished instructions to other circuitry as they continue to execute new instructions. We refer to this as pipelining, so that when we look at the 5 instructions, or 5 instructions can be processed at the same time, since we have 5 different stages of our fetch execute cycle. So let me explain pipelining by starting off explaining or reminding you of the 5 steps of the fetch execute cycle. First, we have the instruction fetch, followed by the instruction decode, the data fetch, the execution of the instruction, and the result return. Now, each of those 5 stages in the pipelining process are going to be stacked up with new instructions that follow each of the stages as a stage is complete. For example, in clock cycle 1, or tick 1, the instruction 1 is fetched. In tick number 2, instruction 1 is decoded and instruction 2 is fetched. In tick number 3, instruction 1, data is fetched. Instruction 2, the instruction is decoded. Instruction 3 is now fetched. In tick number 4, instruction 1 is executed. Instruction 2, the data is fetched. Instruction 3, the instruction is decoded, and instruction 4 is now fetched. Instruction number, or tick number 5, the result is returned for instruction 1. Instruction 2 is being executed by the ALU. Instruction 3, the data is being fetched. Instruction 4, the instruction is being decoded. And instruction 5, the instruction is being fetched. Continuing on to tick number 6, instruction 1 has now completed. Instruction 2, the result is being returned. Instruction 3, the ALU is executing. Instruction 4, the data is being fetched. Instruction 5, the instruction is being decoded. Instruction 6, the instruction is being fetched. And then we move to tick number 7. The result is being returned for instruction 3. Instruction 4 is being executed. Instruction 5, the data is being fetched. Instruction 6, the instruction is being decoded. Instruction 7 is being fetched. So you get the idea. We're continuing to pump new instructions into the pipeline every tick of the clock of the CPU. And it's by this high speed that we're able to produce so much speed in terms of what the computer can do in both doing complicated things and also multitasking and being able to apparently do more than one thing at the same time. So let's take a look at how we view software. There's actually multiple stages. First, we talk about the computer at its level. It's a very confusing view of software because, as we talked about earlier, programs are simply zeros and ones in the form of an object file. They're just long sequences of 4-byte words, and they might look like these here. And of course, we know them to actually be things like this add, where we take the value that's located in RAM memory 20 and the data in RAM memory 24, add them together and store it back into RAM memory location 20. Now, a program like this, again, is possibly complicated in terms of zeros and ones, and no human can actually look at these zeros and ones and understand what the computer is being told in terms of its software commands. So the next level up of expressing software is something that is designed to be somewhat more human-friendly, and this is called assembly language. Assembly language uses letters and normal numbers instead of binary numbers so that people can better understand it, but it's still very cryptic. Let me have you take a look. Here is some assembly language. This is a mnemonic for branch if greater than 0. And what's happening is there is a register that is being examined to see if it is greater than 0, and if this is true, then we jump to the label do it. Another example is load immediate. We're telling the computer to go to a register location on the CPU and load a value of 1 into it. So again, these are very cryptic mnemonics, but they are a lot better than just zeros and ones in terms of understanding how the computer is programmed. But most computer programming is done today with high-level programming languages such as JavaScript, C++, and I guess to some extent even Scratch could be considered a high-level programming language. Here's an example of JavaScript. So we have more English words that we recognize immediately. For example, we have the word function, advance, we have the if and the else, which we've talked about in the Scratch programming language, so we have some concept of what's happening here. If inside the parentheses something that's being tested is true, then we're going to do this statement. Else, we're going to do this other statement. So the very little bit that we've covered with Scratch programming helps you to some extent understand what's going on here at a high level language using JavaScript. Of course, the computer doesn't innately understand JavaScript. So when we write our English level words for code, they have to be converted through a process called compilation into the assembly code that we were looking at earlier, and then further assembled down into zeros and ones for the computer to actually be able to run them on the electronic circuits, which is what constitutes the computer itself. Operating systems are the software that have a special purpose for the computer by managing the resources of the computer. It also helps in the process of booting the computer and managing devices and connections to the internet and things like that. Programming basically, as we've talked about already, uses graphical user interfaces in order to build programs, and programmers typically will take existing programs and add more complexity by adding functions to them. So nobody actually generates programs from scratch, but rather they take existing programs and add new things to them in order to work within a operating system. So in summary, the fetch execute cycle is the main activity loop in a computer, and it repeats over and over sequentially at incredibly high speeds. The cycle, again, consists of fetching an instruction, decoding it, retrieving the data associated with it, performing the operation, and then storing the results. And this is just what's happening over and over, millions of times a second, as the computer executes. This is a cycle that is hardwired into the control system of the computer. It's all based on the actual electronic circuits. Memory, if you recall, is a long sequence of bytes, each with an address to identify it, so that we can randomly select memory locations that can be used to load the ALU in order to make computations. Input and output devices are interfaced as peripherals through the input-output units of the computer so that humans can type information into the computer and see results on the screen as output. So machine instructions do not refer to data directly, but refer indirectly through references to memory locations. Programmers must create complex computations in layers, building up simple operations from basic instructions and then more complex operations on the simple ones. Programmers use sophisticated programming languages to create operating systems as well as complex application software. The basic idea of integrated circuits are integrating active and connective components fabrication by photolithography and controlling connectivity through the field effect, which is done with chemicals. So the book obviously has more detail in Chapter 9 about the process of creating integrated circuits, but it's not really a big focus for me on this class. So thank you for your time.